Dear team makers, my name is XinhuiTang, and my teammate is DaSun. In this project, I'm responsible for two functions: autocomplete the location name and calculate shortest path. First, autocomplete the location name. Time complexity is all 1. The key point here is to traverse the whole data to record locations whose prefix match the given partial name. Here's my code. For calculate shortest path, time complexity here is O of n squared. Here I use digestion algorithm. Digestion algorithm uses the strategy of greedy algorithm. First, we need to initialize a vector which stores distance from source to other nodes. In every iteration, we extend a new node which has the shortest distance from source and update the distance of its neighbor. Once we extended a node, its shortest distance will never change. When we extended all the nodes, we can get shortest distance to every other node. Here's my digestion implementation. There are two more tricks here. The first trick is we can set a map to record nodes precursor node. In this way, we can find paths. The second trick is to decrease running time. We can break the digestion loop once we find the shortest distance to destination node. I also implement bare-method algorithm. The time complexity is O of number of vertices multiplied number of edges, but I find it consumes too much time, and I need to do more improvement. Let's let my teammate introduce.
Hello, my name is DaSun, and I implemented number 2 get position this function, and I use a pair of double to store the latitude and longitude, and I use an iterator to traverse the data map to find the target location. If we just find that name, we just return the ID corresponding to that location, and use the function of get latitude and get longitude we just implemented before to get the output pair. If we just not found that location name, we just set the pair to be -1, and the time complexity here is O of n. And number 4 is traveling children's. And first is brute force implementation. Its idea is from generating permutations, and I'm using DFS and backtracking here to realize all possible paths. And I'm using pruning here to finding that the current costs have already bigger than minimum cost to save some time complexity here. And when we're just reaching the last node, we accept a new path if and only if its cost is less than current cost, and to keep our output vector path to be in descending order, and the last output path to be the shortest path. And we'll return the shortest distance, and along with all the paths when generating shorter paths. What's interesting here is I use to map input location IDs from string to int, and vice versa. To use my adjacent matrix, I use an adjacent matrix to store all my data, and in the vector its index is int. And the time complexity here is O of n factorial. And on the right is my implementation here. It's animation. And the second one is to opt. And a complete 2-opt local search will compare every possible valid combination of the swapping mechanism. First, we generate an arbitrary path, and we just iterating every 2 nodes and swap them to generate a new path. And each time we compare the new path with the current path. If its distance is less than current path, which means it's an optimum, and we just update the current path and update the minimum cost. And then start from number 3, again, just iterating 2 nodes again and again, until we have swapped all the possible pair of nodes. And when we find there's no improvement on our total cost, we just exit the algorithm. And this algorithm just can get a local minimum instead of global optimum, since it is heuristic. And the time complexity here is O of n squared. And on the right is my animation here. Okay, so I think that's all for our presentation, and thank you for your listening.